Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into Fortune's algorithm for generating Voronoi diagrams. It's a fascinating, albeit challenging, algorithm.
I've heard whispers of its complexity. What exactly is a Voronoi diagram, and why would anyone want to generate one?
Great question. A Voronoi diagram partitions a plane into regions based on proximity to a set of points, called sites. Imagine drawing circles around each point. The boundaries where those circles meet define the regions. It's incredibly useful in procedural map generation. For example, creating realistic-looking terrain or city layouts.
So it's all about proximity. Makes sense. But Fortune's algorithm, that sounds intense. What makes it so difficult?
The difficulty lies in its efficiency. It's an O(n) log n algorithm, which is pretty good for computational geometry, but the implementation is notoriously tricky. The author even admits it's a beast to tackle. It involves a sweep line that moves across the plane, creating and managing parabolic arcs, which represent the boundaries of the Voronoi cells.
Parabolic arcs? That sounds advanced. What's the role of these arcs?
Exactly. The arcs are defined by the sites and the sweep line. The intersection of two arcs represents a point equidistant from the two corresponding sites, a point on the Voronoi edge. The algorithm cleverly tracks these intersections and manages the beach line, which is the frontier of all active arcs.
A beach line? This is getting more colorful. So the beach line is like a dynamic boundary?
Precisely. It's constantly changing as the sweep line advances. The algorithm handles two types of events: site events, when the sweep line encounters a new site, and circle events, when arcs collide, creating a Voronoi vertex. Managing these events and updating the beach line is where the complexity lies.
So it's not just about finding intersections, but also about managing the dynamic nature of the beach line. That's a lot to keep track of.
Absolutely. The algorithm uses a priority queue to manage events, ensuring that events are processed in the correct order. It's a delicate dance of adding and removing arcs from the beach line, calculating intersections, and generating Voronoi vertices and edges.
And what about the data structure used to store the final Voronoi diagram? I've heard about something called a DCEL.
Yes, the doubly connected edge list, or DCEL, is a common choice. It's a sophisticated structure that efficiently represents the vertices, edges, and faces of the Voronoi diagram. It's designed for easy manipulation and traversal of the diagram's topology.
So it's not just the algorithm itself, but also the data structure that adds to the complexity. I can see why the author recommends using a library for most applications.
Exactly. Unless you're dealing with a very high volume of large Voronoi diagrams, the effort required to implement Fortune's algorithm might outweigh the benefits. Simpler, O(n)² algorithms or readily available libraries are often a more practical choice.
It sounds like a great learning experience, though. Understanding the intricacies of Fortune's algorithm would be a significant accomplishment.
Absolutely. It's a testament to the elegance and power of computational geometry. While challenging, mastering it provides a deep understanding of spatial partitioning and algorithmic design. And don't forget the visual appeal of the resulting Voronoi diagrams. They're truly beautiful.
I agree. Thanks for breaking down this complex topic for us.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Join us tomorrow for another deep dive into the fascinating world of technology. Goodbye.
Bye-bye.